We now move on to the last part of permutations and combinations, which is combinations. And as we have discussed until now about permutations, in permutations, the order does matter, right? If we have person L first and then person P, that is different from having person P first and then person L, right? However, for combinations, these two are considered the same because we only are looking at selection. How many people were selected? It doesn't matter in what order they were selected, but it just matters that they were selected. And so there is going to be a slight difference. The number of people who are selected are going to be lesser than the order of the people that we can have. And so what we see is when we are talking about a combination of R objects from an object, so we have n total, and we want to choose R of them, then we say n choose R. And as you see, there is that same NPR here. But what else do we have is that it's divided by the number of places that we have, sort of nullifying the different arrangements that we can have of those items. That's what the combination formula is. And so we can look at an example where we are differentiating the two, where we have in A, how many ways can you choose 3 letters from A, B, C, D, E? So there are 5 objects and we are choosing 3, which gives us a total of 10 objects, which you can also do in this formula where you have 5 factorial over 3 factorial times 5 minus 3 factorial. That gives you 10. This, by the way, the NCR can also be represented as a bracket, as we have seen in the pure 1 topic of binomial expansion. We see this introduced there as well. In the other question where we are talking about the arrangement of those 3 letters, what we have is 5P3, which is 5 permutation 3, which is just 60. And what this is there are 10 possible choices of those 3 letters. And those 10 choices are these 10 possibilities. So those are the 10 possible choices we can have, which is the combination part of it. Then each of these can be arranged in 3 factorial ways. Right? So what we have for our permutation is 3 factorial times our 10, which are the total number of choices that we can have for that group of 3 letters, which then gives us 60 from here. We look at an example. In how many ways can 3 fish be selected from a bowl containing 7 fish and 2 potatoes? So what we have is 7 fish. So there are 7 total objects. And we are choosing 3 of them. So we have 7 combination 3, which is just going to equal to 35. So there are a total of 35 ways that 3 fish can be selected from a bowl containing 7 fish and 2 potatoes. Obviously, the 2 potatoes are irrelevant because these 3 fish do not require anything from the potatoes. We're just choosing the 3 fish from those 7 fish that we have. Next, in how many ways can 5 books and 3 magazines be selected from 8 books and 6 magazines? So firstly, we're choosing 5 books from a possible 8. So we have 8 total books and we're choosing 5 from there. Then we have 6 total magazines and we're choosing 3 from there. And because we're selecting both with the and not the or, we will be multiplying these two. Therefore, 8C5, which is 56, multiplied by 6C3, which is 20, will give us 1120. So there are a total of 1120 selections that we can have if we're selecting 5 books and 3 magazines from a total of 8 books and 6 magazines. Because we are choosing them at the same time, that's why we multiply instead of add. Next, permutations and combinations can both be used to calculate probabilities for certain events, where the probability of an event happening is the number of permutations of that event over the total possible permutations that are there. Similarly for combinations, the probability of an event happening, of a choice in this case, is the number of combinations of that event divided by the total number of possible combinations. Let's look at that with an example. There are 15 identical tins on a shelf. None of the tins are labeled, but it is known that 8 contain soup, 4 contain beans, and 3 contain peas. If 7 tins are randomly selected without replacement, find the probability that exactly 5 of them contain soup. So what's happening here is that we're going to be choosing 7 tins out of a possible 15. So 15C7. There are a total of 6,435 possible selections that we can have of the tins. There are these many different ways we can select those tins. From them, what is our success events? That exactly 5 of them contain soup. So from those 7 that we select, we want exactly 5 to have soup. That means we want to choose 5 of them out of the 8 that have soup. Then the other 2 have to not have soup. Therefore, I have to have 2 from the possible 7 that don't contain soup. And because we want these happening at the same time, we will multiply the 2. This will give us 1,176 selections where there will be exactly 5 tins with soup and exactly 2 tins that don't have soup, so either beans or peas. And when we want to find the probability here, these are our success events because they have those 5 soups, and these are our total events because they are all the possible choices that we could have had, or all total possible combination of choices that we could have had. So we get 1,176 divided by 6,435, which will be the probability of exactly 5 out of the 7 selected tins being soup, which is about 0.183 as our probability. Next example, a girl has a bag containing 13 red cherries and 7 black cherries. She takes 5 cherries from the bag at random. We have to find the probability that she takes more red cherries than black cherries. So, the total possible choices that she has, which is just from picking 5 cherries out of a total possible 20 cherries. So 20 C5 are all the combination of choices that she can have of those 5 cherries. This gives us 15,504 total possible combinations of those choices. From that, you want to find the probability that she takes more red than black. So for that, she can have 3 red and 2 black. She can have 4 red and 1 black. Or she can have 5 red and 0 black. And for that first one, 3 red cherries from a total of 13. So 13C3 multiplied by, because you want her to have those 2 black cherries in the same selection, multiplied by 7C2. So 2 black cherries chosen from a total of 7 black cherries. For the other scenario, we have 13C4, because 4 from the possible 13, multiplied by 7C1, because 1 from the possible 7 black cherries that are there. And finally, we have 13C5 multiplied by 7C0. 5 cherries from a total possible 13 and 0 black from a total possible of 7. The first one gives us 6,006. The second one gives us 5,005. The third one gives us 1,287. So all of these 3 are the possibilities of our combination of our cherries from our selection that do satisfy our successful events. And so we either have 3 red, 2 blue, or 4 red, 1 blue, or 5 red, 0 blue. You see how we use the word or, which shows that they are different scenarios that are all successful. which means we're going to add up those total combination of choices that we have. So 1,287 plus 5,005 plus 6,006, which ends up giving us 12,298. These are going to be our successful events. Then to find the probability, you take your successful events, divide by the total possible events, which is 15,504, which ends up giving you 0.793 as your probability of you having more red cherries than black cherries when you collect 5 cherries from a total possible 20 cherries where 13 are red and 7 are blue. We see an example now that says a minibus has seats for the driver and 7 passengers as shown below. And when 7 passengers are selected in random order, we have to find the probability that 2 particular passengers, A and B, are sitting on the same side of the minibus for part A, and for part B, opposite sides of the minibus. So for part A, we have to find the probability that they are sitting on the same side of the minibus. Now here what we can do is we have the 2 sides, right? We have side 1, which has 4 seats, and we have side 2, which has 3 seats. So we have 4 seats here, and we have 3 seats here. When we want to find the probability, we need to find the total events first, which we will also use for part B. And since we have 7 passengers in total, this is including our passengers A and B, 4 of them will be chosen for the first set of seats inside 1, and the other 3 will be chosen for the second set of seats inside 2. So the total possible choosings or choices are as follows: 7C4 times the remaining people after those first 4 are chosen, which is going to be 3C3. And this gives us a total of 35. So there are a total of 35 ways that we can choose the passengers in side 1 of the bus as well as side 2 of the bus. Now we want to keep them on the same side of the minibus. So we either have them both in this side 1 or we have them both in side 2. So we have the first setting or the second setting. This now leaves us with 5 passengers. And for the first scenario, 2 spaces inside 1 and 3 spaces inside 2. And in the second scenario, 4 spaces inside 1 and 1 space inside 2. So again, we're going to choose the passengers for those following seats. In scenario 1, from the 5 passengers, we're going to choose them for 2 spaces. Then we're going to be remaining with 3 passengers. And we have 3 seats remaining. And so we have 3, choose 3. 3 objects or 3 passengers for 3 seats. That's for scenario 1, which is this scenario here. For scenario 2, we have again 5 passengers. Choose 4, because there are 4 options of seats in the first side, multiplied by the remaining, which is 1 person, and we have only 1 choice of seat for him, which is in the second group. This first scenario gives us a total possible number of combinations being 10, and for the second scenario, it's going to be 5. And for the probability, where we take the total successful events, so 5 plus 10, 15 total events that are successful, which means just on the same side of the minibus, divided by the total possible events that are 35, which ends up giving us, so the probability here is going to be 3/7 for the passengers A and B being on the same side of that minibus. And remember, because they are just 2 sides, the opposite of them being on the same side is that they are on opposite sides. So there are only 2 options here. Either A and B, same side, or A and B, different side. And remember how the probability of an event plus the probability of its complement is equal to 1. And these two are complements of one another. And therefore, the probability of them being on the same side is 3 over 7. Therefore, 3 over 7 plus the probability of them being on different side for part B is equal to 1. Which means the probability of them being on opposite sides would just then be 4 over 7. So same side 3 over 7, opposite side 4 over 7. This is the final example, and I'm going to solve it in two different ways. For part A, we are told to find the number of ways of choosing three letters that contain at least one O from the word crook. So we have to choose a three-letter word. Firstly, what are the total ways of choosing that three-letter word? We see that because we have 5 letters, we want to choose 3 from there. We'll have 5 combination 3, which gives us 10. Now, yes, something to note is that these are not all unique. The reason why is because we have 2 O's in our word. Just keep that in mind for now. But these are still the possible choices that we have. Then remember, if we want to choose the letters that have at least one O, then we can use the complement method. Where if you want at least one O, then we find the case that has no O's, then we subtract it from the total. So the case that has no O's, which is just from the letter CRK, so 3 letters being chosen for 3 spaces, which gives us 1. And that tells us that there is one choice only that does not have any O, which is the choice of CR and K, which tells us that 9 of those choices have at least one O. However, again, this is not all unique. And we'll see where that uniqueness comes from. So this is the first method of solving it. And the second method will tell us exactly how many unique ones are there as well. So if you want at least one O, we either have one O in our word, or we have 2 O's in our word, or our selection for that matter. And we will be remaining with the 3 letters that are C, R, and K. The reason we don't include the O's for that first scenario is because if we do end up selecting that O, we just end up with that second scenario, which then would give us an overlap, and we don't want to double count things. And that's why whatever we have in our scenarios, we will remove that letter from our possible choices of letters to use. And so we just have C, R, and K. For the first one, we have 3 letters, and we're choosing 2 out of them. So we have 3C2. For the second one, again, we have 3 letters, and we're choosing 1 out of them. We have 3C1. This first 3 combination 2 gives us 3, and 3 combination 1 gives us also 3, which then when added together, we get a total of 6 possible ways of choosing 3 letters. These are all going to be unique. So where did that extra 3 come from? Well, remember, when you're choosing one O in the one O scenario, we initially have 2 O's in our word crook, and we are choosing one of them to come to the space. And so in this case, what we will have, the total actually possible ways of selecting from this first scenario, where it has 1 O, is actually 3C2 times 2C1, which tells you 3 times 2, which gives us 6, where then 6 plus 3 gives us 9, but not all unique. Why? Because we have the repetition. Remember, ORK, where the first O is chosen, or the second O is chosen, are both going to be the same. Which is why the actual unique ones are just 6. 3 from the first one that are unique, and 3 from the second one which are unique. So the number of ways of choosing those 3 letters, they're just 6 possible ways of choosing them. but there are 9 times that that choice happens. So 6 possible choices, but 9 times out of 10 total number that choice has at least one O, which directly gives us our answer to part B, which is the probability of choosing those 3 letters, where we know that we have a total of 10 choices we can have, obviously not all unique, but 10 possible choices that we can have. From those, 9 are successful that have at least one O, which gives us this as our probability for choosing those 3 letters that have at least one O from that word.